So let's get started. So one thing is already Dr. Sudarshan gave a very good introduction, and I just want to add one or two things. My voice is not clear. Guys, just let me know if my voice is not clear or anything. Is it fine now? Okay, okay, all right. So basically, Dr. Sudarshan will be taking the courses from more of a system perspective, okay, using Laplace transforms and all the other mathematical methods. My part of the course would be to deal more with the circuit side. Okay, so circuits, of course, are the backbone. I don't want to go through all of them. The thing is, like, your training in network analysis, also in circuits, should teach you how to predict or understand the way in which a circuit works. Okay, even without doing a very lengthy, extensive analysis, you should know how to do the lengthy, extensive analysis also. And on the other hand, you should also have an intuitive understanding of we how a circuit would work. So that's why I said you should learn how to predict the output of a given circuit to a certain degree. You can't do a very accurate prediction; that is not possible. But so simulations help us in verifying our calculations. So as you would see, probably not in this course, but like as you go to more complex circuits, you end up with very complicated equations where you need a simulation. And then finally, the proof of the pudding is in eating it, and so measurements tell us whether it is correct or not. Okay. Now, if you take any circuit, just keep it in mind. You might be a little new to these terms. You will see what is called as time domain behavior and frequency domain behavior. Okay. Basically, you will be encountering these terms as you progress through your engineering course. So if you take a circuit, okay, time domain means if you connect it to an oscilloscope, look at the waveforms, how does it behave? Okay. If there is a square wave, how long does it take to rise? What is the rise time? What is the slew rate and all those things? Okay. How do things look like in an oscilloscope? That's the kind of thing that you talk about in time domain. Basically, that is the part that I will be taking. Okay. The frequency domain analysis is what Dr. Sudarshan is taking. That is like if you want to plot the frequency response. Okay. How does the circuit behave for different frequency inputs? That is what is your frequency domain analysis. So there is a lot of tie-up between the two. Okay, something in time domain will impact something else in the frequency domain and vice versa. Okay. Now, what are the tools? So this is a fundamental engineering subject. Of course, this was already covered. Now, I just want to show you this one. So today, not today, in my part of this course, we will be looking at these topics. Okay, we'll be looking at the mesh and nodal analysis. We'll just network theorems. We'll just brush up. I Let me hear from you guys. Like, how much have you guys covered? Like in the first semester, all of you are familiar with the KCL and KVL. Yes. Okay. So all of you have done nodal analysis, mesh analysis for DC circuits. Okay. For AC circuits, have you done the what is called as the steady state solution, steady state analysis? Have you done that? You hope so. Okay. Let me see if you haven't. Okay. So like you have not done things like Okay, somebody has unmuted their mic. Can you please mute it? Like you can just open and talk. Okay, thank you. So because there's some feedback coming, some kind of an echo coming in. Okay, so we'll just do a review of these things. Okay, today's class will basically be a review of some of these topics. Then we'll go into basic RL and RC circuits and RLC circuits. We'll look at filters. Sinusoidal steady state analysis. It is actually in your first semester syllabus, but as we go through it, you can tell me which part you have already covered and which part is not yet covered, and based on that we will adapt. Okay. Magnetically coupled networks, transformers, and so on. Have you already studied in your first semester? Yes. Okay. Only transformers. Okay. Right. Okay. So we will look at it in greater detail. And finally, we'll also cover two-port network theory. Okay. There is what is called as Z parameters, Y parameters, H parameters, and so on. So we'll cover those things. Okay. Filters is a very wide, vast topic, and we'll see how maybe the filters might come to the end. We'll see how we can handle it. Okay. Now, evaluation has been already done. This I have already covered. Yeah, so in my part of the thing, I would like it to be interactive. Interactive in the sense that this part of the course, what I will be teaching, you need to learn how to solve the problems. Okay, so even during the class, you will be solving a lot of problems. Okay, so I would suggest that every time you come for class, please have a proper notebook and also your scientific calculator. Okay, hopefully you have the one which has this the option where you can solve simultaneous equations. Okay, I think the 991 ES and even the MS should have, I believe. So it will be very handy. Even today's class we will be doing some calculations. So if you don't have your calculator with you, you can just step out, grab your calculator and be back. Okay, and the other because it is you learn this subject by, sorry, someone had a comment. Oh, that's really bad, man. Okay, that is true. Okay, that's also true. Okay, maybe you guys can find some online calculator or something where you can solve simultaneous equations. I think you guys can easily figure it out. Guys, if you're putting anything in the chat box, okay. Oh, most of you have not brought it today. Okay. Yes, I had mentioned that you're having, is it distorting my voice today as well? No? This is fine? Right, okay. Okay, so, yes, I'm recording already. Okay. Now, okay. So please, I think you guys can definitely find some good online calculators or some Windows apps or something like that, or where you can, solve simultaneous equations. Okay. Yeah. I mean, whatever you want to use, you can use. Okay. At the end of the day, I want you to be able to do quickly, able to solve equations and problems quickly. Okay. All right. Now, I'll try to give you assignments every 2 weeks, and I'll not be asking you to submit those assignments, okay, because I really don't have the time to go through 67 assignments, okay. But what we will be doing is, as we mentioned the other day, from what has been given in the assignments, maybe with a slight twist or maybe change of numbers, whatever it is, we'll have some quick tests. Okay, it's not a surprise test, but we'll announce it. We'll probably have some 2 or 3 tests, and that will count for your internals. Okay, so I would encourage all of you, please solve the problems along with the class. And in case some of you are listening to the recording because you are not able to attend live, please make sure that you solve those problems. That is how you learn it. Okay. At a slightly later point of time in the class, we'll start using some LT-SPICE simulations also. Okay. And that's what I said. Basically, I have already covered the thing. So don't accumulate your unsolved problems. Okay. You don't solve problems, you'll have a poorer understanding of the subject. And, and the other thing is, don't do group work on your assignments. Okay. Try to individually break your head and do the assignment. That is the way you learn. That is the learning process. Okay. Don't sit 2 days before this test that we conduct. Okay. And ask your friend for the solution, and he sends you a WhatsApp message with all the with all the photographs, and then you try to just learn from that. What happens is your learning really becomes deficient. So even if you're struggling, it's fine. That's the learning process. Don't feel bad. That's how it happens. Okay. So you learn the subject by solving problems on your own. You cross check or discuss. If you're really stuck, you can discuss with your friends or maybe your TAs and so on. Okay, but go through that struggle of trying to solve and understand. Okay, so that's it. And all right, so I thought maybe okay, let me continue in the same this one. Okay. So today what I'm going to do is we are going to go through some of the basic stuff. Okay, I'm going to kind of start right from the foundations. Okay, so please don't get bored because a lot of this might be redundant material for some of you, but the intention is that all of you are on the same page, and it's just basically to review it such that all of you are confident. Okay, all right. So let's start with what is the voltage source. So before we do that, first of all, what is charge? See, we know that in nature, okay, we have both positive and negative charges, and these are quantized, right? The basic unit is basically the charge of an electron. Okay, charge of an electron is given as minus 1.602 into 10 power minus 19 coulomb. Okay, same way for a proton or a single positive charge, it is plus 1.602 into 10 power minus 19 coulomb. Okay, now what do we say? What is current and what is voltage? Let's say what is voltage. If you say that I have some black box and I am having two terminals, okay, and I am saying there is a potential difference between the two of, let's say, V1. Basically, what does it mean? Let's say this is terminal A and terminal B. Basically, what we are saying is that there is a electrical potential difference between terminals A and B, and that is equal to V1. B is at a certain electrical potential and A is at a certain electrical potential, but these two potentials are different, and by how much it is different is V1. Okay, so usually we never talk about the absolute potential of any terminal in our circuits. Okay, always it is with reference to another terminal. So voltage is basically the potential difference. Okay, and if you want to go into the basic physics the understanding, it is basically the amount of work done to move a unit charge from this terminal to the other terminal, right? So if you want to move a charge from here to here, what is the amount of work that you do? This is the measure of the work that you basically do. Okay, but in electrical circuits, we say that when we have a voltage source, okay, we say, okay, this is my voltage source. Okay, this is what is called as an ideal voltage source, right? What is an ideal voltage source? Basically, it gives, let's say this is V0. This particular element gives you an output voltage of V0 between the two terminals. Okay, no matter or independent of the amount of current drawn from it. Okay, now even if you leave it open, what is leaving it open? You don't connect anything, it's just staying in thin air. Okay, like for example, you take a battery. Okay, you take a battery, you're not connecting anything to it, but if you were to do an accurate measurement of its voltage, okay, still it will have, let's say, 1.5 volt battery will have 1.5 volt. Okay, now if you put, let's say, a 10 kilo ohm load across the battery, okay, you will have V0 by 10 kilo ohm resistance current which is flowing. Okay, I have not put these things here. Okay, all right. So let's say you do that. Let's say you put some 10 kilo ohm resistance. Okay, now V0 divided by 10k is the current that is going to flow. okay, and even still then it is going to retain V naught, okay. An ideal voltage source will retain its voltage, correct. Now suppose you get a now let's also think about, just give me a moment, actually I prepared it a little earlier, and I think I'll not follow this particular order. It's better to do it live. Okay. All right. So now let's say if you take a battery, okay, let's say we take a battery. Okay, now we are not talking about an ideal voltage source. We are talking about a real voltage source. Okay. Now in a real voltage source, let's say you have a potentiometer. Let's say this is some 1.5 volt battery, the normal AAA size battery or D size battery that you get. Okay. And let's say this is a potentiometer. All right. Now if you were to measure the voltage at this node, let's say you are measuring the voltage at this node across the load. Now what will happen if you take a, let's say this is a battery. Now what happens is, as you increase the, okay, if the x-axis is current and y-axis is, let's say this is V out, let's call it V out, okay. Now what do you think will happen? Some of you can unmute and tell. Let me again explain the problem. You take a real battery, it's not an ideal voltage source anymore, okay. Let's say you take this AA size battery, your 1.5 volt battery, okay, and you connect a potentiometer to it, okay. Now you are starting from a very high value, so the current will be very low. Now as you keep dialing, let's say you're reducing the resistance, so what happens? The current keeps increasing. Now as the current increases, if you were to measure the voltage across this potentiometer, what do you think will happen? It will start decreasing, correct? Kind of, why do you think it will start decreasing? Do all of you agree with it? The others? Yeah? Okay. Now, why is it? Someone tell the answer. Why is it decreasing? Correct. It has an correct. So this battery can be modeled as a ideal voltage source with the internal resistance, let's say R internal, and then you have your R load, correct? Now, let's say this is your V naught. Now, this is how any real voltage source happens, okay? Not only just a battery, okay? Even if you, okay, take a sensor for example, all right? Let's say you take a microphone. Microphone is a sensor, okay? So let's say some microphone is like this, all right? This microphone can also be equivalently modeled in electrical circuits as some Vin with some Rin. Okay, let's say you have some kind of some strain gauge or some piezoresistive based sensor for measuring pressure or force. Everything can be modeled by all sensors. Okay, all voltage sensors can be modeled as some voltage source with a series resistance. Okay, in a battery it is called as internal resistance. In sensors and other devices it is called as source resistance. Basically it's the same thing. Okay. Now, what should be the ideally how would you like this Rin to be? Do you want Rin to be large or do you want Rin to be small? Close to 0. Okay, so Rin tends to 0 in the ideal case, right? Okay, so when we do mathematical analysis, so here if you see, we have represented with this is an ideal voltage source with the input or a source resistance. Okay, now this ideal voltage source can give infinite amount of current. Okay, no matter how much current you draw, it can supply, or even if you don't draw any current also, it will have the same voltage, and this effect has been modeled by this internal resistance. Okay, now let's look at current. Okay, actually in last class, I think for the analog electronics course, one of you had mentioned that I need to increase my pointer size. So I think what you meant was I need to write a little bigger or something like that. I hope this class is slightly better. Just let me know if you are. So the thing is, if you put something in the chat box, I'm not able to see right now. Okay, so please put it in the, just unmute your mic and tell me. Okay. So, okay. So what is current? First, let's say let's define what is current. What is current? Is a flow of, yeah, flow of electrons. It's basically, current is basically the flow of electrons, and the way it is measured is how many electrons flow in the total, or rather, or instead of just saying electrons, we can just say charges, and we can say what is the total charge flow through the cross section of a conductor per unit time. Okay, so all these are definitions that you would have already studied. We're just kind of making sure that our foundations are good. Okay, so current is basically measured as the rate of flow of charge, right? Charge flow through the cross section of any conductor. The conductor can be in any shape. Okay, but how many charges go through that cross section per unit time? Okay, per unit time. And so we write it as I is dq by dt, right? So now what do you mean when we say a current source? Okay, let's say current source. So let's say we have a current source like this. Okay, now what do we mean by an ideal current source? Can you tell me what is an ideal current? So let's say this is giving I naught current. Correct. So irrespective of the voltage across the current source, okay. So basically you can say for all values of V naught, the I out is basically equal to I naught. Okay, let's say it is connected to some network here. Okay, irrespective of whatever be the voltage across this current source. Okay, for all values of V naught, I out is I naught. This is an ideal current source which does not exist in practice. Okay, now what happens is, how do we model a real current source? Correct. So like how in the previous case, we said, if you go to this previous slide, we said that the amount of current that is flowing out of the battery, if it increases, the voltage starts decreasing. Okay. Same here, same way what happens is, if you plot, let's say V naught here for the current source, you will see that the current starts decreasing. Correct. Let's say this is I out. Okay. So this effect is modeled as, let's say this is R out, okay, or whatever, R internal or R in, or okay, whatever we call it as. Okay, this is the way we model a real current source. Okay, now this is a V out. Now how do we express this? Now in this case what happens? I out is basically, okay, I out is basically what? There is a current division, I naught minus V out times R in. Correct. So this is how you model the real current source. Now this is what happens in even some types of sensors. There are sensors which give a current output rather than a voltage output. Okay. Many times what happens is, it is kind of a little difficult to figure out whether, I mean, it is a sensor which gives some output current or voltage. Some of the current, Some of the sensors will give only, cannot provide a large amount of current. They are treated as voltage sources. Some of them cannot provide very high voltages. They are treated as current sources. Okay. For example, you can take some sensor, okay, some sensor block which cannot provide, let's say, high voltages, okay, but it can provide some variation in current. Okay. So those are modeled as, okay, some current source with some internal resistance. Okay. Now, ideally, how do you want this Rn to be? Rn should be low or high? It has to be very high. So Rn should tend to infinity for the ideal case, right? Okay. All right. So now we have seen what is a voltage source, what are current sources. Okay. These are all what are called as the ideal voltage sources, and rather these are all independent voltage sources and independent current sources. Correct. Okay. Now, what is meant by a dependent? So before I close, before I kind of wrap up the discussion on independent voltage and current sources, okay, in your analog electronics course, you'll be looking at ways in which you can improve this output resistance. Okay. So there are techniques, circuit techniques to improve the Rn for voltage sources, voltage and current sources. Okay. To the extent that, you know, you will almost have a flat line. Okay. So here we saw that there is a straightly decreasing line. You can do a lot of other techniques by which you can kind of make it more flat, and then probably only at extreme levels it will kind of go down. Okay. There are, although it's not perfectly flat, slight, very small slope will be there. Okay. But you can kind of do these things with different circuit techniques. Those techniques exist. Okay. But that is something that we'll be seeing in the circuits class. Okay. All right. Now let's talk about dependent voltage and dependent sources. So what are the dependent sources that you have learned? First of all, what is a dependent source? Dependent voltage source or a current source? Have you studied that? Yes. Okay. Yeah. So what is dependent source? Not across it. Correct. Yeah, someone was trying to tell something, but I think your network is weak. I couldn't hear. Okay, so as you pointed out, Vaibhav Sobri, yeah, tell me. Correct. So there are 4 types of dependent sources. I think you would have already studied. Okay. So here we can start with what is called as a voltage controlled voltage source. Okay. Voltage controlled voltage source. Okay. Which means that some other part of the circuit you have defined some Vx, let's say. Okay. And you say that this dependent source is some K times Vx. Alright. So this is a voltage controlled voltage source. So this particular Vx can be defined across some other circuit parameter element in some part of the circuit. Okay. But depending on that voltage, it is not directly equal. It can have some scaling factor. Now, can you tell me what will be this K? Let's call it kV. Okay. What is the unit of kV? Or the dimensionality of kV? It is a dimensionless. Okay, it is dimensionless because the output is a voltage. The dependent parameter is also a voltage. Okay, basically you can say that if you define this as V1, you are basically saying that V1 is nothing but kV times Vx. Okay, so V1 and Vx are voltage parameters, so it is a dimensionless quantity. Okay, sometimes people might put it as volt per volt, especially in terms of an this thing. Okay, for example, you can define an amplifier, an ideal amplifier, an ideal voltage amplifier can be, modeled as this particular element. Okay, for example, let's say you have an amplifier. Okay, this is an ideal voltage amplifier. Okay, now it has a certain Vin defined between this and ground, and you have a certain Vout which is defined between this and ground. Okay, all right, so this can be expressed as, okay, this is Vn, and you have a dependent voltage source which is, let's say the gain is A, so it is A times Vn here, and this is your output plus minus Vout. Okay, so this is your input terminal, this is your output terminal, this is your ideal voltage amplifier. Okay, for your ideal voltage amplifier, okay, what is your input impedance? Your input impedance is supposed to be infinite, right? And what should be your output impedance? It should be 0. Okay, because this voltage amplifier means it is acting as a voltage source, okay, driving something else, right? So for an ideal voltage amplifier, Rout will be 0, and for an ideal voltage amplifier, the input impedance should be high. Why should it be high? We'll kind of deduce from what we did. Let's say we have a real source, okay, this is some real source with some Rn, okay, going into this amplifier that we talked about. Okay, now how can we write its equivalent circuit? We can say that this is some Rn, and let's say this is the okay, I'll just change terminology, let me call it as Rs. Okay, the source, this is the source. Okay, if there is some input impedance for a real amplifier Rin, and I'm giving you this thing A times Vn as defined as across this one. Okay, and let's say this is my Rout. Okay, this is the model of your real, or what shall I say, a real voltage amplifier. Okay, what is a real voltage amplifier? Why did I draw a line here? Okay, right. Okay, what happens? The actual amplifier, I hope you're following what I'm saying. See, this is your amplifier. Okay, a real amplifier. Okay, now what happens is, if your Rn is lesser, then what happens? Rs and Rn will form a voltage divider. Okay, so for the ideal case, you want your Rn to become infinite, so that the entire, let's say, Vn comes across your amplifier. Okay, let's not write Vn, let me write it as Vs. Okay, source Vs and Rs. So entire Vs comes across as Vn. Okay, and then what do? Your Rout should become 0. Okay, for the ideal case, but in the real case, you will have some input impedance and you will have some output impedance. Okay, and this dependent source is one example where the voltage is across the input terminals. Okay, and you model this amplifier as a dependent voltage source. Okay, there are different other applications where you can do that. Okay, is it clear? Any doubts? I'll just pause here because, yeah. Current return where? Okay, so which one are you talking about? So see here, what happens is, are you talking about this one or this one? Second one. Okay, so the current path, if you see, this is how the current path goes. Okay, and here you will basically have some load resistor, right? Let me draw the equivalent, the load can be represented as some load resistor. So this is the next KVL that you draw. This is another loop. Okay, so once you actually, so this is a model, all right. Now what happens is, how do you actually build a voltage amplifier, or how do you actually build an amplifier? We look at it in the analog circuits class. Okay, so there you will see exactly what happens. This is a model, but even in the model, you will see that this is the path of the input side. This is the loop in the output side. Okay. So this is, okay, what you should understand is, this is the model of the real, of a real voltage amplifier. Okay. Now, exactly what sits inside, see, you don't get a dependent source by itself. Okay. It is a one way to mathematically model and analyze a circuit. Exactly what will happen, you need some active elements. You need a BJT or a MOSFET or JFET or some transistor, which will help in, providing the gain and so on. Okay. I think once we look at that, you'll get some clarity. But this is a model. Yeah. Continue. Yes. Yes. Exactly. You exactly got the point. Okay. So the lower the Rin, the lesser the Vin that is available, and this voltage, dependent voltage source, the output also will be correspondingly lower. Okay. Yeah. Which is why it is always important for Rs to be as low as possible and Rin to be as high as possible to get the maximum gain out of this whole thing. Is it clear? The lower the value of Rs, the better it is. The higher the value of Rin of an amplifier, of a voltage amplifier, the better it is. Okay. And same thing here, you want Rout to be as low as possible. Okay. So this particular condition will give you the best performance. Okay, is it clear? Is it clear to everybody? Okay. All right. If there are no other questions, next so this is what we call as a voltage controlled voltage source. Okay. I have kind of used it in the model. I'm kind of hitting two birds with a stone here. Basically, I'm going over dependent VCVS. Okay. Many times you will see people calling this as VCVS. Okay, voltage controlled voltage source. Okay, and we are also looking at the model of an ideal amplifier. Okay, now let's look at what is the model of a dependent current source. Let's look at current controlled voltage source. Okay, what is a current controlled voltage source? So this CCVS. Okay, now basically what is this? This is basically a dependent voltage source. Okay, but whose voltage is controlled not by some other voltage, but let's say there is some other point where there is, let's say, some Ix current flowing. Okay, some Ix current is flowing in some part of the circuit, and let's say this is called as, let's say, R times Ix. Okay, so V out, how do you write the equation? You write V out is given by R times Ix. Now, can you tell me the dimensionality of R? It will be in ohms. Okay, it is basically volt per ampere, or in other words, ohms or resistance. Okay, so here basically it's the same thing. This is a voltage source, and but the voltage depends on some other current which is flowing. Okay, Now, you will see some, if you look at go more into analog design, you will see what is called as transimpedance amplifier. We'll probably do that, or maybe Dr. Anup might cover in the analog electronics part, but just keep it in mind. We have this kind of a thing also. Okay. All right. Now let's look at the other side. Now we looked at voltage sources. You have a voltage controlled voltage source or a current controlled voltage source. Now let's look at the voltage controlled current source. Okay, this is VCCS. Okay, basically what is this? This is, yeah. Can you repeat? I could not hear. You want what? You want an example or? Example, is it? Okay, okay. All right. So, well, I can give you an example, but that will be kind of a little jumping ahead. Okay. There is what is called as, see, there are what is called as a transimpedance amplifier. Okay. I'm just giving you the name. Don't worry about it. You might learn that. Okay. So, transimpedance amplifier, commonly called as TIA. What happens is, if your input source is a current source, okay, let's say you have a sensor, okay, a sensor which gives you a kind of a current output, but you need a current output, but you need to convert it to a voltage so that you can pass it to an ADC and you can digitize it. Okay, let's say you have such a sensor. Okay, now you model this as, let's say this is RS, let's say this is IS. Okay, there is I think you guys are familiar with op-amps. This is basically a simple TIA. You put a big resistor in feedback. Okay. Now this is a simple TIA or a transimpedance amplifier. Now what happens is, there is virtual ground here, right? So the voltage that this is seeing is, so the input impedance is almost zero. Okay. The input impedance of this particular amplifier, the R in, is tending to zero. So all the current kind of flows into this particular circuit, and that current goes across this resistor and develops a voltage. Okay, so V out will basically be, assuming that this is an ideal op amp. Okay, so this is basically a virtual ground. So you will see that entire IS flows here and through RF. So it becomes minus IS times RF is your V out. Okay, this is a transimpedance amplifier. I'm just kind of jumping ahead. Now, how can you, this is basically, can be represented as a current control voltage source. All right. So basically this amplifier will have, if you look at, okay, let me maybe just, so how can you represent this? So this is IS, you have, let's say, RS going into the, we are now abstracting it to a model. Okay, I showed you the actual circuit. Now what is the model? This will basically have some R in, let me not ground it. Okay, and then you have a, let's say, R times, let me call this as I in. Okay, R times I in voltage source with a series this time. Okay, this is your V out. Let's say this is your R out. Okay, is this making sense? So in this particular case, let me draw this properly. Okay, and I in is basically defined as the current which is flowing into this particular circuit. Okay, this red line is basically the model of my transimpedance amplifier. Okay, and for the ideal case, basically you want Rn to tend to 0 so that the entire IS, so that, as we pointed out earlier, In becomes closer to IS, or it as close as possible to IS. Okay, and then R out has to become closer to 0. Okay, so this here R gives you the transimpedance factor, or the it has the elements of ohms, or the dimension of ohms. Is this clear? Okay. All right. Okay. So it's already 10:50, and so I will stop here. We will continue from next class onwards. Okay. Okay. Any other doubts or questions, or we can close for today? Yes. Right. No, you just think. Okay. What is the equation for IN? IN is basically there is a current division happening here, right? So IN can be written as RS divided by RN. Yeah, RS divided by RS plus RN, right? Hello. Yeah, right. So let's say one second. I need to right. IN can be written as IS into RS divided by RS plus RN. Now, if Rn becomes 0, what is In? In is Is into Rs by Rs, which is equal to Is. Okay. In other words, it is like saying you're kind of shorting out this resistor, so the entire current goes into the amplifier rather than the internal resistance. And yes, you are right in pointing out that for a good sensor, Rs should tend to infinity. That we have already seen. No? In a independent current source, you want the RS to be as high as possible. Is this clear? Yeah. Okay. Okay. Thanks, guys. Thanks.